Let's look now at example number 5, which is going to feature an inelastic collision. Inelastic collision means that the kinetic energy of the system decreases during the collision. The objects could stick together, but they don't have to stick together. So we're actually going to look at two different situations where the before situation is the same and the after is different, and compare elastic to inelastic so we can see the differences. So in this situation, I've got a cart moving to the right at 4 meters per second, and then a second cart moving to the left at 6, and again, this one's smaller than this one. And again, as a way to understand, I want to draw a picture of what's happening. So we're told that the two collide such that the 1 kilogram cart, which is this one, is moving to the left at 2 meters per second. So like that one keeps moving to the left and it just gets slowed down. And then we're supposed to figure out what happens to the other one. My guess is that rather than go through the first one, it probably goes to the left as well. My guess is that it'll probably go a little bit faster since this one goes a little bit slower, but again, that's completely a guess. I really can't do that 100% sure just by looking at the picture. So let's calculate the velocity of that cart. By now, hopefully you're catching on to the whole momentum conservation trick. So the momentum of this system is going to be conserved. There's nothing from the outside interfering. Again, I'm going to make right my positive direction. You don't have to do it that way, though. I'm going to calculate the momentum of the first object. So 0.25 times 4. And then I'm going to add the momentum of the second one, realizing that since it's going to the left, I need to remember to make that velocity negative. Again, you don't have to do it that way. You could switch the direction to positive. You just have to be consistent. All right, so if we figure out all the arithmetic here, the stuff in blue is 1 mark. And the motion sensor lights have turned off. Plus, looks like we can still see okay though. That's going to be negative 6 marks. So then when I add those together, it's like negative 5 marks. And of course, since the momentum is conserved, that's going to be my momentum of my system after those two things collide. So in my after collision, equation, I've got 0.25 kilograms, 0.25 kilograms times an unknown final velocity, and then plus 1 kilogram times 2 meters per second, but that's to the left, so it needs to remember to make it negative, and all that's got to add up to negative 5 marks. So this is a good example where everything is moving, both before and after the collision. Writing these equations out is super critical. If you skip these steps, you're going to mess up, and you're not going to be able to figure out where you messed up. So write that equation, show all your work to get to there. Write out this equation, set it equal to that same number. Otherwise, you're not going to be able to make any comparison of this to anything from the previous picture. So, doing a little bit of simplifying and solving here. Stuff in blue is still that. Equals negative 5 marks. I'm going to go ahead and add that to both sides because it's negative. I'm going to do it by adding. So plus 2, because 1 times 2 is 2. So what that means is that the momentum of the first one is negative 3 marks. And so V1 prime would be negative 12 meters per second, or 12 meters per second to the left. That's how I prefer that we write that. All right, so we do the whole thing again. Second trial, the carts are separated and move towards each other with the same initial velocity. So my before picture is exactly the same as it was before. So I don't need to do anything differently. I just need to come down here and go, hey, this system has the same momentum as we did before. Nothing changes there. This time, the 1 kilogram cart is moving at 3 meters per second immediately after the collision. So V1 prime now equals 3 meters per second. And again, we want to figure out what the first one does, the 0.25 kilogram cart does. I'm going to guess that it doesn't go as fast as it did before. So I'm just going to draw an arrow about yay big. And then again, let's do a momentum conservation equation. So P system prime equals 0.25 kilograms times V1 prime plus 1 kilogram times negative 3 meters per second, like that. And that equals negative 5 marks. So again, solving for V1, just like we did up above, I'm going to add the stuff in red to both sides. So negative 5 marks plus 3 meaning that now the first cart, the one in blue, has a momentum of negative 2 marks. So dividing both sides by 0.25 to get V1 prime isolated would give you a velocity of negative 8 meters per second. But I'm going to write that as 8 meters per second to the left. So not as fast as it was going before, because not as much momentum was transferred from the red cart to the blue cart. All right, so now in which situation is the collision between the two carts elastic? Explain your reasoning. Well, our reasoning is real simple. Our reasoning is the change in kinetic energy 0? That's what we're looking for. So I'm not going to work out all the math. Dramatic pause. But using the original information, the kinetic energy of this system is 20 joules. In the first scenario, like in part B, the kinetic energy of the system after the collision is 20 joules. And in the scenario in the second trial, so that was the first trial. In the second, the kinetic energy of the system is like 12.5 joules. So it's kind of easy to go 20 equals 20, not 12.5. So the first trial is elastic because there was no change in the kinetic energy. Exclamation point, because that's exciting. So when we're checking to see if something is elastic, it's just, does this kinetic energy number change? If yes, it's inelastic. If not, then we say it is elastic. And it's as simple as that. So down here at the very bottom, we got a little summary table. Maybe push pause real quick and fill it out, and then press play again. I'll give you 4 seconds. All right, so in all of these situations, momentum is conserved, meaning there's no change in the momentum of the system. So delta P system then would be equal to 0. And in an elastic collision, there is also no change in kinetic energy. In an inelastic collision, we lose some kinetic energy. So delta K will be negative, but in an explosion, we gain it. So delta K is positive. And then if a collision is completely inelastic, we lose a lot of kinetic energy, and the objects stick together. So that's a little quick summary to help us classify these different kinds of interactions. One thing we're going to study later this week is why are cars designed to stick together when they collide? And the answer might kind of come by comparing the final velocity of the first car in these two examples and think, what's better, getting flung backwards at 12 meters per second or getting flung backwards at 8 meters per second? We're going to do a whole lab and investigate that question in a lot of detail. I think that's going to be next class period. So I'll see you then. Until then, ta-ta.